53.09%. That is the brake thermal efficiency. A diesel engine recorded in a certified test in Shandong Province in September 2023. Let me tell you what that means in plain English. For the entire history of commercial trucking, a diesel engine has never converted more than 50% of its fuel into useful motion. The rest bleeds away as heat. Always. 53.09% is not a rounding error. You heard that right. This engine just crossed a threshold no production diesel had ever reached, and that is just the beginning, because the number is not the story. The engineering behind it is. Hit a quick like and subscribe so you do not miss the next one. By the end of this video, you will understand exactly what changed inside that engine, and why it rewrites the ceiling for every diesel truck on Earth. To understand why 53.09% matters, you first have to understand what made 50% feel like a physical law. A diesel engine is not really an energy converter. It is a controlled combustion event with an energy recovery problem attached. When fuel ignites inside a cylinder, the chemical energy releases in an instant. Some of it pushes the piston down and turns the crankshaft. The rest leaves as heat through the exhaust stream, absorbed into the cylinder walls, generated at every bearing surface and piston ring in the drivetrain. The engine does not waste energy because it was designed poorly. It wastes energy because thermodynamics demands a cut. Think of it like a bonfire inside a sealed metal box. You can extract useful work from the pressure the fire creates, but you cannot stop the fire from heating the box itself. The hotter you run the fire, the more aggressively the walls absorb heat, and the harder your cooling system has to work to shed it. Recovering more energy from combustion means more heat attacking the very structure built to contain it. This is the wall the diesel industry ran into, and it ran into it repeatedly. Ricardo Engineering had been refining diesel combustion geometry since the 1940s. Cummins, Bosch, and Mayen each ran dedicated high-efficiency research programs across the 1980s and 1990s, spending hundreds of millions of dollars chasing 50%. By 2010, the best laboratory results from any of those programs had reached 47, 48, occasionally 49% under tightly controlled conditions. Most production engines in global freight service were running between 38 and 42% in real-world operation. Most people who follow engine technology never hear this next part. The 50% ceiling was not a single barrier waiting for one insight to fall. It was a structural constraint built from three separate physical limits: combustion completeness, thermal containment, and parasitic energy loss. And no research program had found a way to attack all three without one solution undermining the gains of the others. The global heavy trucking fleet burns roughly 300 billion liters of diesel fuel every year. At 40% average thermal efficiency, roughly 180 billion liters of energy equivalent leaves those engines annually as waste heat. Not as motion. Not as freight delivered, just heat rising off a tailpipe. The industry consensus was not that the ceiling was too high to reach. It was that reaching it cost more than it returned. That consensus was about to get very expensive to hold. In 2015, Weichai Power announced it was targeting 50% brake thermal efficiency in a production-viable diesel engine, certified under real-world conditions, not laboratory ideals. The international powertrain engineering community responded with the particular brand of polite skepticism reserved for announcements the industry considers aspirational rather than credible. The Society of Automotive Engineers published commentary that year, noting the thermodynamic difficulty of the stated target. Several European powertrain research directors gave interviews describing the goal as technically interesting but practically remote, given the cost and complexity of the simultaneous optimizations required. A widely cited analysis in a German automotive engineering journal concluded that closing the remaining gap to 50% would require solving problems that had resisted decades of funded research from organizations with longer institutional histories and larger R&D budgets than any Chinese engine manufacturer had yet demonstrated in international certification. This was a rational position. It was based on everything the global industry knew at the time. They said the same thing about combined cycle gas turbines in the 1980s. Every major power generation company had modeled the thermodynamic ceiling for natural gas turbines and concluded that 50% net electrical efficiency was effectively unreachable in commercial operation. General Electric and Siemens both ran programs aimed at it. Both were told by independent analysts that the goal was theoretically possible but practically uneconomical. By 2000, combined cycle plants were running at 58% net efficiency in commercial service. The analysts had been right about the difficulty. They had been wrong about whether the ceiling would fall. The difference was that the programs that crossed it did not refine the existing architecture. They replaced the underlying logic of how the system captured energy. Weichai's program was not a refinement. It ran from 2015 through 2023, 8 years. More than 500 engineers drawn from Weichai's internal research division, Bosch's Fuel Systems Group, and the State Key Laboratory of Engine Technology at Tianjin University. The program did not begin with a combustion geometry target. It began with an energy accounting exercise. Map every joule of energy entering the engine. Trace exactly where it goes, and identify every point where recovery was theoretically possible but practically unaddressed. That accounting produced a list. The list produced a hierarchy, and the first item on that hierarchy was the problem the industry had been treating as a diminishing returns dead end for 30 years, because the first mechanism the program developed did not approach combustion the way anyone outside the program expected. The problem with diesel combustion has always been the shape of the burn, not the timing of a spark. Diesel engines do not use one. The geometry of how fuel meets air inside the cylinder and how completely that meeting converts stored chemical energy into useful pressure on the piston before the exhaust valve opens and the opportunity is gone. Picture a garden hose with the nozzle set to its widest spray. Full pressure produces a broad cone of large droplets that wet a wide area but do not travel far or break apart finely. Tighten the nozzle to its narrowest jet, and the same pressure produces a fast, narrow stream of tiny droplets that travel further and atomize more completely on contact with air. Diesel fuel injection follows the same logic. Finer droplets mix more completely with compressed air, combust more thoroughly, and leave less unburned fuel at the edges of the combustion event. Fuel that would otherwise leave as heat loss and exhaust, particulate, rather than pressure on the piston. Weichai's first core innovation was an ultra-high-pressure injection system developed with Bosch's Fuel Systems division, operating at 2,500 bar, roughly 2.5 times the injection pressure of a standard high-performance diesel. At that pressure, fuel atomizes to droplets measuring less than 10 microns in diameter. A human hair runs roughly 70 microns wide. What entered the cylinder was not mist. It was closer to vapor, but injection pressure alone is not the complete picture. Here's what most coverage of this program missed entirely. Higher injection pressure increases the velocity at which fuel enters the cylinder, altering the fluid dynamics of the combustion event in ways that interact badly with standard cylinder geometry. Weichai's engineers coupled the high-pressure system with a modified Miller cycle combustion chamber, a geometry that closes the intake valve earlier than a conventional diesel cycle, reducing the effective compression ratio while preserving the expansion ratio. The result is a combustion event that runs cooler at peak temperature, cutting thermal stress on the cylinder walls and reducing the heat load rejected to the cooling system by a measurable margin. Tested in isolation on Weichai's bench at Weifang in 2019, the combined injection and Miller cycle system produced a measured brake thermal efficiency of 49.5%. That sat at the absolute edge of what the global industry had accepted as the practical ceiling. This mechanism alone moved the needle further than 30 years of incremental optimization from the world's largest engine manufacturers had managed. But it was not enough, because solving the combustion problem exposed a second energy stream the engine was still throwing away entirely, and the solution to that problem is the part that genuinely should not work. Here's the brutal catch with high-efficiency combustion. The better you burn the fuel, the hotter your exhaust stream becomes. A standard diesel at 40% efficiency produces a diffuse thermal exhaust load. An engine at 49.5% with ultra-high pressure injection and Miller cycle geometry produces exhaust gases that are hotter, faster, and carrying far more concentrated energy. A conventional exhaust system routes all of it to atmosphere. You made the combustion better. You made the waste stream more valuable. You're still throwing it away. The logical response is to capture it. Route the exhaust through a heat exchanger, drive a secondary power cycle, and feed the output back into the drivetrain. The diesel industry had explored waste heat recovery for decades. The problem was always the same. A recovery system adds mass, adds mechanical complexity, and creates parasitic drag on the exhaust path. Every study through the 1990s and 2000s returned the same verdict. The energy recovered did not reliably exceed the cost of carrying and operating the system. The math would not close. It sounds like it should not work. That is exactly why what Weichai's program found worked. The insight was not in the heat exchanger. It was in the working fluid. Conventional waste heat recovery used water or steam, the same principle driving power plant turbines for over a century. Steam-based organic Rankine cycle systems extract energy from high-temperature exhaust, but leave the lower temperature tail of the exhaust curve untouched. Weichai's engineers, working with the State Key Laboratory of Engine Technology, replaced the working fluid with an ethanol-water blend tuned to the specific exhaust temperature profile of the Miller cycle engine. This fluid reaches phase transition at a lower threshold than steam, recovering energy across a wider portion of the exhaust stream, including the range that steam-based systems had always discarded. The system added 47 kilograms to the powertrain. In bench testing at Weifang in 2021, it recovered the equivalent of 3.4 percentage points of brake thermal efficiency. The parasitic drag cost was 0.8 percentage points. Net contribution: 2.6 percentage points on top of the combustion system's output. That is not a marginal gain recovered from rounding errors. That is a second power source extracted from energy the engine had been discarding since diesel combustion was invented. Combined on the bench, both mechanisms reached 52.1%. What remained unproven was whether both could sustain peak performance simultaneously inside a single production architecture, or whether connecting them would cause one to quietly destroy the gains of the other. Two mechanisms that each work perfectly in isolation can destroy each other's gains the moment you connect them. In powertrain engineering, this is not a theoretical concern. It ended more than one high-efficiency diesel program before certification. The interaction problem between Weichai's combustion and waste heat recovery systems was specific and predictable. The Miller cycle geometry is sensitive to exhaust back pressure, the resistance the engine experiences, pushing combustion gases out of the cylinder. Small increases in back pressure shift the intake event and pull combustion away from its optimized state. The WHR system adds back pressure by design as it extracts thermal energy from the exhaust path. In early integrated testing at Weifang in 2021, that interaction reduced the combustion system's contribution by 1.2 percentage points whenever the WHR system ran at high recovery load. The combined result was lower than either system delivered independently. The integration had made the engine worse. The part nobody covers is what the engineering team did next. The conventional response to an integration failure is sequential calibration. Tune combustion first, lock its map, then fit WHR into whatever window remains. This produces stable but permanently suboptimal output because neither system ever hits its actual peak simultaneously. The fixed maps cannot respond to the dynamic interaction between two systems under real load variation. Weichai's team, working with the State Key Laboratory of Engine Technology, built something different. They developed an AI-driven management system designated the WOS, Weichai Operating System, that monitors and adjusts both systems simultaneously in real time. Think of it the way a navigation system manages a city road network during a major disruption, not by following a fixed route, but by reading live conditions across every node and recalculating the optimal path hundreds of times per minute. The WOS monitors 147 engine parameters: exhaust temperature, back pressure differential, intake manifold pressure, fuel rail pressure, and WHR turbine inlet conditions among them, and adjusts injection timing, Miller cycle valve events, and WHR bypass valve position at 200 cycles per second. The back pressure interaction that had cost 1.2 percentage points under sequential calibration cost 0.3 percentage points under WS control. The system was not eliminating the conflict. It was anticipating it fast enough to compensate before the loss propagated through the combustion cycle. In the first fully integrated test under WS control at Weifang in March 2023, the system recorded 53.1% brake thermal efficiency. The institution running independent verification asked for the test to be repeated, then asked for it a third time. Here's the honest picture. 53.09% is a certified result achieved under specific conditions. Steady state load, at optimal operating temperature, with premium grade diesel fuel meeting European EN 590 specification. It is not a figure every truck running this engine will match in daily service. Cold start performance with the WHR system thermally inactive sits closer to that of a conventional high-performance diesel. The manufacturing cost premium over a standard Weichai heavy-duty engine runs between 18 and 24% at current production volumes. Retrofit into existing truck platforms is not feasible. The WOS architecture and WHR system require co-integration from the powertrain design stage, not installation into an existing chassis. These are real constraints. Anyone modeling commercial adoption timelines needs to hold them. Now here is what the certified result actually means. The independent verification was conducted by the China Automotive Technology and Research Center, CATARC, one of the accredited bodies whose test protocols are recognized under the UN Economic Commission for Europe's Vehicle Regulations Framework. The test ran 3 times across 2 separate test cells. All 3 results fell within 0.04 percentage points of each other. The certified figure, 53.09%. The prior certified world best for brake thermal efficiency in a production-viable diesel engine was 51.1%, held by a Jacobs Vehicle Systems research program developed in collaboration with the U.S. Department of Energy's Supertruck Initiative, a program that required 11 years and more than $50 million in federal and industry co-funding to reach its result. The gap between 51.1 and 53.09 is 1.99 percentage points. In efficiency notation, that reads as marginal. In fuel and emissions terms, it is not. That is not a refinement of the prior result. That is a different category of engine. A heavy-duty truck on a standard long-haul duty cycle burns roughly 23,000 gallons of diesel per year. A 2 percentage point efficiency gain saves approximately 460 gallons per truck annually. Across a fleet of 10,000 vehicles, a mid-sized logistics operator by global standards, that is 4.6 million gallons per year. The CO2 reduction, calculated under the Intergovernmental Panel on Climate Change's transport emissions methodology, runs to approximately 42,000 metric tons annually for that single fleet. If that figure surprised you, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover what this result does to the global trucking sector's energy and investment model. The ceiling did not bend. It broke. Heavy trucking carries approximately 70% of all freight. By value in every major economy, it also produces roughly 36% of global road transport CO2 emissions, while representing less than 5% of registered vehicles. The International Energy Agency's 2023 Transport Outlook treated diesel thermal efficiency improvement as one of the 3 highest leverage interventions available for freight decarbonization, alongside electrification and route optimization, and based that analysis on an assumed achievable ceiling of 51% by 2035. That baseline is now obsolete. Here is what genuinely shifts when a certified efficiency ceiling moves by 2 full percentage points. Fleet operators in long-haul freight make capital allocation decisions on powertrain technology based on total cost of ownership across a 10 to 12-year vehicle life. In Europe, where diesel fuel taxes average roughly $1.40 per liter, the annual fuel saving per truck at this efficiency level produces a payback period on the manufacturing cost premium of 4 to 6 years at current prices, well within the asset life of a long-haul tractor. In Southeast Asia, where fuel subsidies are progressively being reduced and electrification infrastructure for long-haul routes remains limited, the economics shift further toward high-efficiency diesel as the available near-term solution. The International Road Federation estimates that long-haul fleet replacement cycles in these markets run 7 to 10 years on average, meaning adoption timelines are constrained not by willingness but by the pace of natural fleet turnover. The number that most analysts miss entirely is how difficult this result is to replicate. A patent covers a design. It does not cover the 8 years of simultaneous co-development between a combustion geometry, a working fluid formulation, and a real-time management system that required all 3 to be optimized in parallel to produce the certified figure. The WOS calibration maps were built across more than 40,000 hours of bench testing. A competitor acquiring the patent acquires the blueprint. They do not acquire the institutional knowledge encoded in those maps. This is precisely the pattern that played out with combined cycle gas turbine technology in the 1990s. When General Electric certified the first CCGT plant above 55% net efficiency in 1997, competitors had access to the published thermodynamic principles within months. It took most of them between 8 and 12 years to match that result in commercial operation. Not because the science was withheld, but because the integration knowledge resists transfer on paper. The limit was always technical. Every decade that passed without this result was a decade spent treating an engineering problem as if it were a physical law. What 53.09% actually means is larger than one engine program and larger than one certification event. For 130 years, the diesel century ran on a consensus. More than half of every drop of fuel burned inside a compression ignition engine was simply the thermodynamic price of doing business. That consensus shaped how freight infrastructure was designed, how climate models assigned emissions, cost to surface transport, how engineers at the world's largest powertrain companies drew the line between an ambitious target and a theoretical one. It was not a failure of imagination. It was a reasonable reading of every result the industry had produced up to that point. This result proved the reading was wrong. Not incrementally wrong, structurally wrong. If you made it this far, you now understand more about diesel thermal efficiency than most people who write about it for a living. What was actually demonstrated in Shandong Province in 2023 was this. The three physical constraints the industry had long treated as separate and fixed, combustion completeness, thermal containment, and exhaust energy recovery, are a single connected system. Manage all three simultaneously with enough resolution and speed, and the ceiling that held for a century does not hold. The ceiling was not one wall. It was three walls leaning against each other. Move all three at once, and they fall together. That is what the WOS architecture proved. In a production-viable powertrain running on a test bench in an industrial city, most people could not place on a map. What the global industry does with that proof is the open question. Every major engine manufacturer now knows the ceiling is higher than their programs assumed. Every fleet operator, modeling total cost of ownership, has a new efficiency reference point that was not in last year's analysis. Every energy agency forecasting diesel demand across the next 2 decades has a certified result that changes the slope of every projection they have published. Industries built around a constraint for half a century do not recalibrate quickly, but they do recalibrate. If this changed how you think about diesel engines and what they are still capable of, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Is 53% thermal efficiency the beginning of diesel's second era, or proof that the industry should have accelerated electrification a decade earlier? Both positions have serious engineers behind them. I read every single one. See you in the next one.